Thank you very much, Andy, and thank you also for the invitation. I'm really honored to be here and to give this memorial lecture. I did not collaborate with John during my time here in Liverpool, but I do remember him very well from coffee breaks, from lunch breaks, all the discussions we had about astronomy, about the world in general. So, yes, he's very dear to my heart. So, as Andy said, I come from Slovenia and I prepared this talk, Stars Gone in a Day. I will talk a little bit about what I was doing here after I left, but still with the Liverpool John Moore's Gamma Ray Burst group, and also what I'm doing a little bit now with tidal disruption of stars by massive black holes. So, Slovenia, I don't know if you all are familiar where it is in this map. It is a small country here. Next to Italy, Austria. We like to say that we are on the sunny side of the Alps, and I don't know how many people you know from Slovenia, so I picked two persons that you maybe know. So if you're in sports, in basketball, this is a famous basketball player, Luka Doncic from Slovenia, now very famous in the United States. And if you are more into good food, then I would recommend the Ana Roche restaurant with 3 Michelin stars. Yes, so just a little bit of advertising for Slovenia. So I come from a Center for Astrophysics and Cosmology at the University of Nova Gorica. These are my colleagues. Some you see we are a bit senior, and then we have quite a lot of postdocs financed also by a European co-found project called SMASH, which focuses on using machine learning in astronomy and other sciences. And we also have quite a number of very enthusiastic PhD students. I would like to mention that we are now currently 25. And when I prepared this talk, I counted, and I think we come from 12 different countries. So I'm proud of this international community. We, in our center, we focus, I would say, on high-energy astrophysics, so not just stars and what we see usually in the sky, but things which like make bang or come with large, have large energies like cosmic rays, gamma rays, and so on. And we are also part of several international collaborations in this respect. I will talk more about that, about Vera Rubin Observatory later in my talk, but my colleagues also work in Cherenkov telescope array, which is a special kind of, these are special kinds of telescopes. So I would say that I work on astrophysical transients. So these are things that change in the sky. So when we look at the night sky with our naked, eyes, we would see what we would see. We would see stars, we would see Milky Way, we would see some planets in our solar systems. And if we would observe the sky night after night, we would see that basically the sky does not change. It only rotates. It slightly moves, but otherwise the stars, the bright stars, appear in the same order, the same shape of constellations from night to night. So they don't change because first they are very far away. So even if they move relative to us, they are so far away that we don't notice this on time scales of years or hundreds of years, or even thousands of years. And the other reason why the sky doesn't change is because stars live for a very long time. They don't just appear or disappear in our human lifetime. So basically the night sky remains, looks eternal. However, even back in the days before the invention of telescopes, people did notice that sometimes it seems that there appears a new star in the sky. They would call it nova, or if it was very bright, they would call it supernova. So we have, for example, from the records of old Chinese astronomers, we have evidence that for example, they observed a bright supernova in year 2054, which was so bright that apparently they could read during the night time outside without any additional light. So these supernovae do appear, and the more we observe, the more supernova we see. So they saw with naked eyes maybe one every now and then, which was bright for a few weeks, and then it would fade away and disappear. But with telescopes, we can see deeper into the universe. We can see fainter objects, so we see deeper, and therefore we can see more of these supernovae. And here you see an image. This is the projection of our night sky on the plane. This is our Milky Way plane. And we see that supernovae appear everywhere now and then. In some parts of the sky, you will see that they appear more often than in others. This is not because this part of the universe would be different, but it is because we are observing, there were surveys that were observing this part of the sky more regularly, and therefore they detected these changes in the sky, these supernova explosions, as we call them today. So the more we observe with better telescopes, which go deeper in the space in the universe and cover larger areas of the sky, the more of these supernovas we detect. But it's not just supernovae. Nowadays, we know that there are also other transients, as we call them, things that appear and disappear on human-friendly timescales, let's say. So we see that there are several types of variable stars. Maybe you see that this one a little bit twinkles. There are different objects, for example, also active galactic nuclei with accretion disk around supermassive black holes. Then we also know that some objects, some stars, appear to change brightness, but they don't really change brightness intrinsically, but they just appear because of the geometrical effects. For example, if we have a star in the background and another star which comes just between us, if we are here, and the star in the background, this star can act like a gravitational lens, so it can focus light from the background star so that it appears brighter for some period of time, and then it goes back to normal. And then we have these catastrophic events, which when a star changes brightness due to some event which destroys the star. Such events are the supernova explosions that I mentioned, and also there are several special types of supernovae. I would call a special type of events which are similar to supernovae, which are gamma ray bursts, and I'm going to talk a bit more today. Tidal disruption events, stars torn apart by massive black holes. And then there are also other transients, things that appear, like brief flashes in the sky, for example, in the radio wavelengths, we call them fast radio bursts, or in X-rays, so fast X-ray transients, which we do not know yet what actually produces them, but could be that they are also linked to these catastrophic events connected with stellar destructions. So for today, I'm going to talk a little bit about supernovae, and mostly about gamma ray bursts and tidal disruption events. And to do so, I'm going to first give you a very brief course of stellar evolution, just in 13 slides, so bear with me if you already know all this, so that we will then better understand gamma ray bursts and in particular. So what are stars? We often draw stars like that, but they don't have these spikes. They're round, so they're spheres made out of gas, hot gas. They're mostly made out of hydrogen. 3/4 of their mass is hydrogen, 1/4 is helium approximately, and there are only a few % of other higher elements in the periodic system. The two main characteristics of stars are, first, that they are held together by gravity, so they are not held together by forces between molecules or something like that, like we are, but they're held together by gravity, and therefore they are round, because this is the best shape for the gravity, the lowest energy shape. So they are round, or let's say roundish. They can, if they rotate fast, they can be squashed a little bit on the top. Then the other characteristic is that they, at least in some period of their time, they produce energy in nuclear reactions. When they fuse together, for example, hydrogen to helium, this would be the first stage of these nuclear reactions, but then they can go also to higher fusion reactions, fusing helium to carbon, and so on. So these are two main characteristics. So how do they form? They form out of molecular clouds of gas and dust, mostly made out of molecular hydrogen and helium. So these clouds are very cold. They have very low density. But still, because they are large, they can, due to self-gravity, start collapsing. And when they do that, they also start, when they collapse, they also fragment. So this is a nice numerical simulation where you see the gas. First, it was homogeneous with the same density everywhere. And now you see these yellow dots popping up, which are denser parts of this cloud. So the cloud fragmented in smaller parts, which are now collapsing even further. And you will see little yellow dots appearing, which are protostars. So these are these are parts of this gas that collapsed individually, formed this roundish shape. And these protostars will collapse even further, and they will turn into stars. When they will be hot and dense enough in their cores, they will start nuclear reactions, and then they will turn into real, proper stars. So you see here that we have stars which are always born from a large cloud of gas. So they're always born in groups, in families. They never form alone. And when they form, so we have a large group of stars, thousands, hundreds of thousands of stars. They can have different masses. They are of different types, as we say. So most of stars that form in such a cloud are low-mass stars, and also which are also colder on the surface. And then very few are very massive stars. So it goes down from about 8% of the solar mass to about 150 solar masses. So these are hot, but these are very rare. And these are colder, but very common. Also, our sun is, for example, of type G. What we also know is that they live different amount of time. So they spend their life in this main phase when they're fusing hydrogen to helium, producing energy, shining brightly. They live very different amount of time. Massive stars like this one can live only maybe 10 million years. Then they are so bright, they use up all the available nuclear energy and they die. While these low-mass stars can live several tens of billions of years. For example, our sun is going to live 10 billion of years, and now it's approximately at the middle of this evolution, so it has about 5 more billion years to go. So life of stars, if we would describe it in one sentence, we would say it's a constant battle between gravity and pressure. Gravity wants to squeeze the star as much as possible, down to a single point, which would be then a black hole. But if star is hot, if it has nuclear energy which has been produced inside in these fusion reactions, it is hot and it can fight. This hot gas has pressure and it fights against this gravity. So we have, our sun is now in a stable period of time when this gravity and pressure are in equilibrium. But as time goes on, when the star uses up all the energy available, it also cools, it has no source of energy anymore, but because it is hot in the cold universe, it emits energy. So it would start to cool. And this is then bad because if it cools, then the pressure drops usually, and then it's in a normal, ideal gas, but then the star would collapse due to gravity. So the gravity would win this fight. So we'll come to this. When we talk about the final stages of the stars. So low-mass stars like our sun, when they use up all the available nuclear energy, the core would collapse to something which is called a white dwarf, an object. This is an object of the size, for example, of our Earth, but with a much higher density. For example, like if we would take our sun and squeeze it to the size of the Earth, which means about 100 times lower radius, we would get a white dwarf. So initially, the low-mass stars like our sun, when they are going along this evolution, they would expand, the envelope would expand into a giant red star, but the core would collapse, and then in the end, to make it very short, this envelope is so thin and rare that it eventually escapes in the universe, in the space surrounding the star. So we would call this phase a planetary nebula phase. And then when this clears out, we are only left with a white dwarf. So white dwarf is the end state of the evolution of low-mass stars, because the pressure in these objects is sustained by some special type of gas, which we call degenerate gas of electrons. And this has a special property that it still has pressure, although it cools down to very low temperatures. So this can then sustain this fight against gravity. We have a slightly different story when we talk about high-mass stars. For example, stars which have more than 8 solar masses. When they reach the end of the lifetime, so that they use all the energy, nuclear energy available in them, the core collapses to something even denser than white dwarf. But this releases so much gravitational energy that the envelope of the star is ejected, and we call this a supernova explosion. So this is just an animation of such explosion. First, we would see this explosion just as a star which became much, much brighter. But if we look years later, many years later, we would see this nebula, this gas that is being expelled out of this explosion. So this is the remnant. This is the nebula which was left over after this supernova explosion in 1054 that Chinese astronomers observed. So they observed only a little dot in the sky, which then disappeared. But later now, if we take telescopes, we see this nebula, this explosion expanded into such a cloud around it. And somewhere here in the center, we have the remnant, which is the remnant of the core that survived. And in this case, this is a neutron star. So neutron star is in a way similar object as a white dwarf, only that it is even denser, smaller and denser. It has a mass, it has radius only around 10 kilometers and a mass about 1.4 or 2 solar masses. So the density of neutron stars is so high that it's basically higher than the density of atomic nuclei. And it is much higher than anything that we can produce in laboratories on the Earth. And perhaps you heard that some neutron stars can be also are pulsars. So when they are young, they can rotate very rapidly, and they have strong magnetic fields. And if the direction of the magnetic field is not aligned with the rotational axis, then this light that they are emitting along the magnetic field lines oscillate. So we have this precession of these jets, and if one of those jets shines directly towards us, it is in our line of sight, then we would see this pulse, the light that usually it would be the normal light, and then suddenly something brighter and brighter and brighter. So these pulses gave name to this type of objects, pulsars. So this can be a remnant of the core of a massive star. However, if the core of this remnant core has a mass which is higher than the highest possible mass for the neutron star, then the core would collapse to a black hole. So this would be left after the massive star. So what is a black hole? We would call this a part of the universe where the gravity is so strong that nothing can escape from there. That even light, which has the highest possible velocity, 300,000 kilometers per second, cannot escape. So we do not know what is happening inside this part of the universe, because no information, no light, no electromagnetic signal, nothing can come out of the black hole. And in effect, these black holes are quite simple astrophysical objects, because we can just say, okay, if it is not rotating very much, then we can say that it has a radius which is called Schwarzschild radius, or event horizon, and it is given by this equation where g is the gravitational constant, m is the mass inside the black hole, and c is the speed of light. So it's the more massive the black hole is, the larger the radius. It just scales linearly. So for example, if we would aim to make a black hole out of our sun, we would have to squeeze it from current 700,000 kilometers radius to just about 3 kilometers. On the other hand, even if we go to larger masses of black holes, as we will encounter a bit later today, for example, 10 million, million solar masses, the black hole would still be quite small, just about 4 times the size of our sun. And even the most massive black holes that we know in the universe, about several billion solar masses, would be comparable to the size of our solar system, which is very tiny compared to the size of our galaxy. For example, our solar system is maybe several light hours large, but our galaxy has 100,000 light years in diameter. So they're very small. So the stars can leave behind these small black holes with a mass of several solar masses, maybe 10 solar masses. So to bring together all this stellar evolution, I said that we have, so here is the small masses, small stars, and then the mass of the stars goes upwards in this diagram, and then this is the timeline, let's say. So low mass stars like our sun, as I said, they go first into red giant, then they become planetary nebula, and a white dwarf is left behind. More massive stars explode as a supernova, and they can leave behind a neutron star or a black hole. What I didn't tell you is that there are new findings now that some stars, some very massive stars, can explode. This explosion can be so violent that nothing would be left out after the star, so even the core would be destroyed. So this is one possibility. This is still not completely confirmed, as far as I know. And the other possibility is also that some stars can actually be failed supernovae. So when the core collapses to a black hole, it fails. The star fails to explode, but this envelope just shrinks is sucked into the black hole. So such a star would just go and disappear. So this is, again, there are some papers which claim that they have observed this, but it's of course difficult to prove that it actually went into a black hole. So this is the stellar evolution in this basic, let's say, form. But then there are one more additional interesting thing is that we have also something that I would call a different type of supernova, or also we could call it a long gamma ray burst. So here we have an animation of a star at the end of its life, massive stars, maybe also rotating, and the core collapses to a neutron star or a black hole. But now the star doesn't explode in all directions immediately, but first 2 jets drill from the center of the star, and they expand into the surrounding media with almost the speed of light, and they produce these 2 bright jets. And if one of those jets points toward us, we see this as a gamma ray burst, as a short burst of gamma rays, maybe lasting from somewhere from 2 seconds to several hundred of seconds. And then it disappears. These were very mysterious sources, maybe 50 years ago when they were first detected. But later on, we did find out many things. So one of these things is that they occur in other galaxies, that they are stellar explosions. Why do we have this? Sorry, let me see. Why does this star not explode in all directions in the same way, but it has these 2 jets? Because if it is rapidly rotating, then the material which is when the core collapses, the material which is in the equatorial plane has rotational energy and cannot fall in the black hole directly. But it does. But all this collapse produces gravitational energy which wants to escape somewhere. But then, so here it cannot escape because there is a lot of material around in the equatorial plane. However, along the rotational axis, material does not have so much rotational energy. So it gets sucked into the black hole or to the neutron star. And here we have, let's say, less dense material. So all the energy which is released in the gravitational collapse finds the way out through this, along the rotational axis, through these jets. So this is why it's a different type of supernova. We think that the rotational energy makes the difference. So These gamma ray bursts are nowadays detected by satellites, such as Swift satellite, Swarm satellite. So they occur randomly in different parts of the sky, in all the directions, basically. Unexpectedly, we cannot predict when they are going to occur, but satellites detect their positions. And if we look at the same place in the sky, they send us back to the Earth immediately the coordinates where this explosion happened. And if we look there with the optical telescopes, we can see that there is something called an optical afterglow at the same place in the universe. We will also see it here, I think. And you will see here the light that appeared and disappeared. And if we look closer with better telescopes to fainter sources, we still see that there is a source which is fading away. So this is what we observed with the Liverpool telescope here at Liverpool John Moores University with my colleagues. So thanks also to Chris and the others who set up the Liverpool telescope it still has automatic response to these alerts. So when a gamma ray burst occurs in the universe and it is detected by a satellite, the satellite directly sends to a specific network, sends information to the telescope, which then stops whatever it was observing. It slews in less than 1 minute to the position in the sky where a gamma ray burst occurred and starts observing this optical afterglow. So this was really revolutionary at that time, 20 years ago, when we first started doing this. And it meant also that we were much faster than the classical telescopes, because we want to catch these afterglows as soon as possible, because gamma ray bursts last only a few minutes, let's say, and we want to observe as soon as possible, because also afterglows don't last very long, sometimes maybe just a few hours or a few days. So every second was important that we got more information about what was happening closer to the explosion. So what we were also very good at, thanks to colleagues here in Liverpool, is to have not only observed the light in a standard way, how bright it is, but also to study its polarization. So we developed a special Ringo polarimeter, which was an instrument on the Liverpool telescope, and then later Ringo 2, Ringo 3, which studied the polarization of light. Why? So if we look at the model of a GRB, so the core of the star collapsed to a neutron star or a black hole, and there we have these two jets drilling through the surface of the star and expanding into the universe. In these jets, we can have internal shocks when matter is colliding, and here the gamma rays are produced, what we see as gamma ray burst. But then here later on, when this jet collides with the surrounding medium, it slows down, and there it is where afterglows, optical afterglows are produced. And we would like to study what makes these afterglows, how important is the magnetic field in these afterglows, and that's why we used the polarimeter to study these events, because as we often say, gamma ray bursts are the most energetic explosions in the universe. We could compare, for example, that gamma ray bursts in a few seconds emit so much energy as our sun will emit in its whole lifetime in 10 billions of years. So they're really extraordinary events. So we wanted to study the role of magnetic fields, and we studied the polarization of light. So if light is actually electromagnetic waves, this tells us how much of this light is, these waves are in the same plane. Okay, I did not explain this now very well, but it's a special technique that tells us about the role of magnetic field. And I don't want to spend too much time on this. For example, we had some very nice results showing that in some cases there is a uniform magnetic field present, which is important for these models of gamma ray bursts. This also led us to receive this lovely prize in 2007. There are some people here that are on the photo today, but yeah, so it was a very nice achievement. So now I'm going to go to mention also other ways to destroy a star. So one is this long gamma ray burst, as I said. Then may I just mention also short gamma ray burst. So these are similar events, but they last less than 2 seconds, so that's why they are called short. And for many years, we did not know what exactly causes them. There was a model theory that they are caused by 2 neutron stars merging. And why do they merge? Because they emit something called gravitational waves, and they lose energy, and they come closer and closer, and when they come close together, they merge, and they also produce a huge explosion with 2 jets going out in the opposite directions. So this was a model for many years, this neutron star merger, and this actually was then confirmed in 2017, when in this special event on 17th August in 2017, when gravitational wave detectors detected gravitational wave event, and satellites detected short gamma ray bursts, and optical telescopes detected optical afterglow in this faraway galaxy. So this is just to say, so this is not actually destroying a star, but it is merging 2 neutron stars and making a larger neutron star or a black hole. But now, if I go back to stellar destructions, I would like to talk about tidal disruptions of a star by a massive black hole. So if these long gamma ray bursts and supernovae are somehow a fate of the star, massive stars will end up its life like that, it cannot avoid it, then tidal disruptions are basically bad luck, stars which had bad luck to come too close to a black hole. So black holes, I mentioned these small black holes which are produced when a star dies, but we have also very massive black holes in centers of most, if not all, large galaxies. So in some, they are accreting, in some these black holes are accreting material from the surroundings. They form an accretion disk, which is very bright, and we call this active galactic nuclei. But in most galaxies, these are maybe 10% of galaxies, but in most galaxies, black holes are there, but they are dormant. They don't say anything, they don't emit any light, so we don't know actually that they are there. We can only know that they are there by the gravitational influence that they have on the surrounding matter. For example, if there are stars orbiting them, or if there is some or gas clouds or something like that. So these supermassive black holes in centers of galaxies have a range of approximately 1 million or slightly less solar masses to several billion of solar masses. But they are still too small that we could actually see them with the normal telescopes. The angular resolution of our instruments is too low, except in these 2 cases that you may have saw in the newspapers. In 2019, this donut was very popular on the internet. It was everywhere. So it was a radio image made with the Event Horizon telescope of a center of the galaxy, active galaxy M87, where we see this shadow. So we see the disk around the black hole, and this shadow inside basically is where this black hole is hiding. And then later, we also saw similar image of our galactic center, the center of our Milky Way, called Sagittarius A star, which is not here in this other galaxy. This is just to show the comparison of the sizes. So this is in our galactic center, but if we would compare the size of this ring with this one, we see that we would have to shrink it. It's much smaller than the one in the M87. But still, it is there, because our black hole is smaller than in M87, and it is hiding somewhere here. And we can see that this is comparable, for example, to the size of our sun, this black hole. But these are rare events. These are only 2 cases where we see the shadow of the black hole. Otherwise, we cannot see the black hole directly. What we see, for example, in our galaxy is also the motion of stars in our galactic center. So here would be this ring that we saw before, this star, and we see the motion of stars around it. And we see that some stars very rapidly turn around here, and from this we can, using the third Kepler law, we can calculate how much mass there is. And also in this way we get that there is about 4 million solar masses black hole in the center of our galaxy. In other galaxies we cannot see these surroundings of the central black hole in so much details. So in some we know, some we can still manage to measure the velocities of stars, the average velocity of stars and so on. In some we don't know. But what it can happen is that one of those stars comes too close to a black hole. For example, what if one of those stars would come close to the black hole? It could be that if it comes close enough, it will be torn apart by tidal forces. So what are tidal forces? I'm sure you're familiar with the tides. So if we look at the system Earth, I apologize for Slovenian words, it's from my textbook for Slovenian students. So if we look at the Earth's oceans, this is exaggerating, of course, their size here, and the moon, because moon is attracting this part of the oceans or Earth with larger gravitational force than the other part, which is further away, because gravity is such a force that it decreases with the radius, with the distance. So if we go in the center of the Earth, how does this feel? For Earth, it feels that like it was torn apart. It is torn in these two directions, in the direction towards the moon, but in opposite directions. So something similar, this is why we have tides on the Earth. But what if we take that instead of the Earth we have a star, and instead of the moon we have a black hole? Black hole is also acting with its gravitational force on the star, pulling this side with higher force than the other side, and elongating it like that. But what if the star comes even closer to the black hole? This elongation is even stronger, so it can be that this force, the tidal force, overcomes the self-gravity which holds together the star, and the star is destroyed. So this is a basic picture that we have about these tidal disruption events, as we call them, from Martin Rees, Royal Astronomer Martin Rees from 1990. So he said, okay, if the star comes inside this tidal radius, as we call it, of the black hole, so if this is a black hole, this would be some kind of radius, a sphere, in which if the star comes too close, inside this sphere, it's going to be torn apart by these tidal forces. If it stays outside, it's safe. So we can say that this tidal radius, the distance where these things become serious, is given by this equation, where this is the mass of the black hole, mass of the star, and radius of the star. And we can measure how serious, let's say, the impact or the encounter is by this parameter beta, which tells us how much closer do I get only to this, do I just scratch the surface of this tidal radius, or do I get even closer, and then the star will be even more disrupted. So this is the basic picture is that if we take a star on a parabolic orbit, half of the material will be on bound orbit, half on unbound orbit, so half of the material the star will get disrupted, half of the material will then return eventually to the black hole, and half of the material will escape. This is a very simple picture. And what we also need to know is that this works. The tidal disruption occurs only if this tidal radius lies outside of the black hole, so that the star is disrupted outside, not after it already enters the black hole. So here I will show you a hydrodynamical simulation of my former PhD student, Tai Jankovic. So here is the black hole, sorry. The black hole is blue, sorry. Then it is this white dashed circle is the tidal radius, and this is a star at the beginning of this simulation. So as we start the simulation, you see that the star was disrupted in a long stretch, in a long, let's say, spaghetti. And now we are zooming out to see better. We will see that part of the material will return to the black hole. Now it is some part of the material turns to the black hole and winds around here, around the black hole, while part of the material escapes. So this star was on our parabolic orbit. That's why we have this exactly like Martin Rees, his simple model predicted. So what happens now is, as this material circles around here, it's hot, it makes a gas accretion disk around there, and this means that unfortunately, we cannot see this process that well, the process because it is too far away in other galaxies. But what we would see is that the galactic center, the center of a galaxy, would become brighter because of this. Because of the, okay, this is too much, but as the material comes back, we assume very simply that this gravitational energy, that as it comes back, is transformed to luminosity. And then this would then predict, again in very simple model by Martin Rees, that the luminosity, the brightness of such a galactic center would decrease with time as a potential law with t to the minus 5/3. So this is, as Martin Rees already predicted, if something like this happens in a galaxy, we could actually detect, this would actually be a signal that there is a massive black hole in this galaxy. And we could also, in a way, if we know exactly if we understand and can model such events very well, we can then also use these events to measure the black hole mass in these galaxies. So these events were indeed observed. Some were observed already in X-rays already in the 90s. For example, like this one, here we see this decrease with t to the minus 5/3. But then in optical and ultraviolet light, they were starting to be observed a bit later. For example, here we see a galaxy in 2009, some distant galaxy. We don't even see the galaxy now, but here we see that something became brighter. And looking more in details, we can see that there was a galaxy before which got brighter, and then later it faded away. So these are tidal disruption events. We have now about 100 of these events observed. We can deduce, let's say, that on average they would occur one such event per 10,000 galaxies per year. And they show this, let's say, decay with t to the minus 5/3, approximately, not all of them exactly the same, but this is again a challenge to model. What we still do not know is where the light is actually coming from in these events. For X-rays, we know that they are coming from this accretion disk around the black hole. But from the optical, we don't know whether they are coming from, it seems like it's not coming directly from the accretion disk, but maybe it's coming from some envelope, where the X-rays from disks are then reprocessed to optical and UV light. Or maybe there are some models which show that the optical light is coming from this cross section. So when the self-crossing, where the material, as I will show in the next movie, crosses itself and becomes very hot at the cross self-crossing. So this is a similar simulation as before, only that this time the star is not on the parabolic orbit, but elliptical. So all the material will come back to the vicinity of the black hole. So we will see now. So the star is disrupted, and material will return to the black hole. And you can see that now this material is colliding with the incoming material stream. So we have a very hot spot here. And so this could be a source where the optical light is coming from. So this is something that we would still like to study further with observations and also with numerical models. So we see this disk forming around, and then eventually material will either fall into the black hole or escape in the surrounding space, and this will then fade off such an event. So there are many things we would like to know. Also, what is the type of the disrupted star? What are the mass and spin of these black holes? How frequently tidal disruption events occur? in what types of galaxies do they occur. They occur in different types of galaxies, but prefer some galaxies more. And of course, we would also like to study many things, including the role of magnetic fields, multi-messenger sources, also gravitational waves from such events, and so on. So as I said, I will try to be brief. So we have about 100 tidal disruption events known today, but we expect that we will discover many more with the Vera Rubin Observatory, which is just beginning to start the legacy survey of space and time in Chile. So it's a great telescope with the observatory with a special design, which enables it to have a very large field of view. So here it is field of view of this telescope compared to the size of the full moon in the sky. And at the same time, as it has 8.4 meter mirror, it can also detect faint objects. So it covers a large part of the sky and it goes deep. So it can discover many objects. It will operate for 10 years, scan the sky. So this part of the sky, such large part of the sky, it can cover in one exposure in 15 seconds, and then move to the next one, and the next one, and the next one. So it can cover 1/3 of the sky visible from Chile in one night, and it's going to repeat this in 3 nights, the whole sky, and then it's going to repeat this for 10 years. So this is just an image showing comparing the field of view of this observatory compared to, for example, James Webb Space Telescope or Hubble Space Telescope. So they're quite much larger. So this is the picture of the telescope. As I said, it is already operational. We had some nice images. We saw first nice images in June this year. And this is just to give you an idea. This is just one little part of what it is going to do. We can see the number of objects, the detail that it can show. So we are really excited, not just in astrophysical transients, but in different research areas of astronomy about what this telescope or this legacy survey of space and time is going to bring us. Their estimates is going to observe 20 billion stars and 20 billion galaxies and 17 billion stars, so which is about 20 times more than are currently known from the Gaia satellite. So this is the legacy survey of space and time, as I said, for 10 years, every 3 nights in 6 different filters. The data set will serve different science cases, but I'm personally mostly interested in transients, as you saw, and especially in tidal disruption events.
The universe is a dynamic place, but how do scientists spot changes in the cosmos? First, they need to know what stays the same. Every night, Rubin Observatory will capture new images of the sky. Over time, scientists combine the many images of an area of sky, producing a template image of how that area typically looks. When new images are taken, the template image is subtracted, pixel by pixel, leaving only the changes. A technique called difference imaging. Whether they're flashy like supernovae, on the move like asteroids, or pulsating like variable stars, Rubin will find about 10 million things that change every night in an epic feat of spot the difference.
Yes, so we did some simulations, and we think that it's going to, among these 10 million transients per night, there are going to be about 10 to 20 tidal disruption events. So it's going to be like looking for a needle in a haystack to find those. But if we do, that will be great, because we will have many more known than we know today. In just a few months, we will discover more than are known today, and we can study all these topics that I mentioned before. So just to conclude, I would like to mention that the neighbor of a Rubin Observatory, just 25 kilometers, is El Sauce Observatory, where we have a small Go Chile telescope, which is I discussed with Andy. It's, of course, not even close to your national school's observatory, But this is for Slovenian students. It's remotely operated, a 40-centimeter telescope with a smaller piggyback telescope. And we are very happy that we are offering this to our students and also high school students. So I just want to mention also this, because I'm really happy that we have such a project for younger generations. And just to conclude, I'm going to leave you with this promotional video of the Vera Rubin Observatory.
The night sky, our window to the universe beyond. Immense, mysterious, powerful, quietly beautiful. Cosmic events at the edge of our imagination unfold in the darkness, ready to be discovered. When we look at the night sky, we see into the past. Untold stories carried through space by light, the great historian of the cosmos. Technology has evolved over centuries, allowing us to look farther, to the edge of our horizon. We invented telescopes to explore and cameras to capture these traveling messages. Yet the changing cosmos remains unseen. A new telescope opens its eye and captures it all. The objects that move and those that flash, even those we cannot see with our eyes. Every few nights it covers the sky, finding all that has changed. And within minutes, new glimmers of activity are carried around the earth to anyone waiting to explore them. What will you discover that no one has seen before? It's time to find out.
Thank you.